Hi, Dr. Brian Walsh here. Right now, I'm in the middle of Central California on this whirlwind tour with my family of 7 in an RV, driving around the U.S. in what we're calling the Functional Medicine and Family Tour. Now, if you haven't heard of this before, or even if you have, it's a 2-day weekend seminar on the best of what functional medicine has to offer about mitochondrial dysfunction, detoxification, glucose dysregulation, in ways that you've never heard about, I promise, as well as in-depth evidence-based information on blood chemistry interpretation from a functional medicine perspective. Now, I know this information is really great, but I have to be honest, feedback from attendees, from the hundreds of people that have already gone to this thing, is beyond what I could imagine. People love this weekend, and I think there's a good reason for that, and I want you to go too. So, but if you're on the fence about it, or if you're just not sure, I totally get that. So what I'm gonna do right now is show you with one marker exactly what you get when you go to this weekend seminar. The first thing you're about to see is something that we call the pre-event learning videos. Now, this was over 5 hours of pre-recorded videos on the physiology of the blood chemistry markers in the first place. Now, this is something that's usually not taught in the functional blood chemistry space, unfortunately, but it needs to be taught, because once you know the markers and how they work physiologically, then interpreting them makes so much more sense. Now, I have been told that these pre-event learning videos are easily worth the cost of this entire weekend just by themselves. They're that valuable. So I'm going to show you one little piece of this 5 hours of pre-event learning videos on a particular marker. Then I'm going to come back, and I'm just going to go ahead and show you all the slides that I have in the weekend seminar for this particular marker. So you get an idea of exactly what it is that you're going to learn when it comes to this blood chemistry interpretation, functional medicine, and family weekend seminar. So hang tight, let's watch the pre-event learning video on bilirubin, then come back and I'm going to show you everything that I have on bilirubin from the weekend seminar, so you know exactly what you're going to get when you go to the functional medicine and family weekend seminar.
Here's bilirubin. I mentioned this before, but red blood cells, they have a shelf life of about 120 days. They eventually go into these awesome, again, like little barrel-like things inside the spleen. They're old. They have sort of denatured proteins. They're not as young and flexible as they are. Funny how that kind of goes in life. And they're not as flexible, so they get stuck. And then the resident macrophages, which is this thing here in blue, gobbles up these decrepit red blood cells, and basically recycles everything. The whole red blood cell gets recycled. Phospholipids get broken down, and any proteins that were, or enzymes turn into proteins, amino acids goes back into the amino acid pool. Everything gets recycled, including hemoglobin. Hemoglobin gets broken down into heme and globin. Globin's amino acid or a protein gets broken down into amino acid. Heme, this is all inside the macrophage. Heme gets converted into biliverdin via the enzyme called hemoxygenase. Needs reducing agents and oxygen, which I think is actually very important, reducing agents. Makes biliverdin. Biliverdin then, still inside the macrophage, gets converted into bilirubin via and I didn't write it, a zinc-dependent enzyme called biliverdin reductase, so that's zinc. Biliverdin reductase, now you have bilirubin, which then goes into the bloodstream, and this is said to be in the indirect form or the unconjugated form. Now, how do you know it's unconjugated? Well, because you have to hear the rest of the story. That bilirubin then goes into the liver, eventually makes its way to the liver, where it goes through the phase 2 detoxification or biotransformation pathway called glucuronidation. Glucuronic acid is added to bilirubin. It's still bilirubin, it just has a luggage with it now. So now bilirubin with its luggage is glucuronic acid, because it's glucuronidated. Bilirubin then leaves the liver. Now that's the conjugated form or direct form. So you have 2 forms essentially of bilirubin. Now some labs will separate this for you. Some labs you have to ask. If you have total bilirubin on a blood chemistry, it's a combination of indirect or unconjugated bilirubin and direct or conjugated bilirubin. The majority of it's going to be unconjugated, I believe, but we'll talk about that part as well. And then, now that bilirubin's ready to head out, has got its luggage of glucuronic acid, goes into largely the biliary tree coming out of the liver with bile, it's what supposedly gives bile its pigmentation, and then goes into the intestines. And there's more to this in terms of urobilinogen and some other things and recycle. But then bilirubin in the bile gets essentially pooped out. Okay, it gets pooped out of the body. Good. So that's basically the physiology of it. So once again, if bilirubin is high or low, I would like to try to figure out what could be causing that. Let's do the low one because that's pretty easy. Now, red blood cells are always breaking down. It would be strange if somebody was not breaking down their red blood cells. That would be, in my opinion, some severe pathology of some sort. And I don't think that's even really talked about much in the literature. So I'm going to rule that out. Someone has low bilirubin on a blood chemistry. So that's probably not it. Theoretically, if the liver can also do this too, break them down, by the way. But primarily the spleen, if the spleen weren't working properly, then perhaps that would do that, or the liver and the spleen, but they'd have so much pathology that would be a big issue at that point. So what else could cause low bilirubin? Well, right here, first of all, if you think about it, if you picked up on this is a zinc-dependent enzyme. That means that biliverdin reductase, if it doesn't have zinc, is not going to work properly. That means you can end up with biliverdin, which is not bilirubin, and when a lab is looking for bilirubin, it's looking for bilirubin, not biliverdin, and so it won't find bilirubin because it's all sort of caught up as biliverdin because of a zinc deficiency. The other bit that I've mentioned in webinars, but perhaps not with these videos that you've seen, is bilirubin is an antioxidant. It is a lipophilic, fat-loving, fat-soluble, if you will, antioxidant. And I didn't write it here, but essentially what bilirubin does, actually we can do that. So let's say here's the phospholipid membrane of any given cell. Now we have this bilirubin. Bilirubin swings past this phospholipid membrane, donates electrons, becomes biliverdin again. Well, that's fine, because as long as we have some reducing agents, NADPH, biliverdin reductase, and some zinc, it can turn back into bilirubin as an antioxidant and continue to act as a fat-soluble lipophilic antioxidant. Well, what happens if you have a lot of oxidative stress? Understand that when a lab is looking for bilirubin, it's looking for bilirubin. But if bilirubin donated its electrons for oxidative stress, and now it's biliverdin, the labs aren't looking for biliverdin. They're looking for bilirubin. And so as they look for bilirubin, it's not there. The reasons why could be severe liver and kidney and spleen dysfunction, I suppose, zinc deficiency, or possibly excess oxidative stress. Then on the other hand, what about if bilirubin's high? I want to think about that. And we're talking about total bilirubin. If bilirubin's really high, maybe red blood cells are being broken down too fast. If that's where it comes from, maybe they're being broken down too rapidly, faster than they're supposed to be, called hemolysis. Well, that's cool. That would make sense as to why bilirubin was high. Which type of bilirubin would be high? The unconjugated form or the conjugated form? They both might be a little bit high, but if it's spilling out too fast and the liver can't keep up, then the unconjugated or indirect would be pretty high. So that's one. Another potential cause of high bilirubin is liver dysfunction, and it's severe liver dysfunction. But let's say the bilirubin is not getting conjugated fast enough. It's going in here to collect its suitcase, but it can't. Say at the airport, there's a line going in there. Because the airport's broken down, it's going to be this long line on the outside of bilirubin people waiting to go and get their luggage out of the airport. And so because of that, it's all going to be built up on the outside. Now you can easily say, well, what would be the problem with that? It'd be way too much unconjugated bilirubin because the liver's dysfunctional and it's not getting conjugated. On the other hand, let's say bilirubin was high, and where did I say that it went? It goes out of the liver basically as bile. Well, what if there was some kind of obstruction going on here? What if, and I'll just use red again, what if this was obstructed? Bilirubin isn't getting excreted. And again, and I hope if this is even mildly confusing to you, just watch it again and walk yourself through this again, because I want you to understand these. This is how this works. If bilirubin's high, maybe it's too much red blood cell breakdown, you'd look around at some other parts of the lab. Maybe it's because the liver's not working well, it's not conjugating things very well, and you'd look around at other things on the lab. Maybe the liver's working just fine, but as it's trying to leave the body, it can't because there's an obstruction of some kind. Then if it can't leave, then it's going to be high. And again, you'd look around at other places on the lab, things that we've already talked about, by the way, like ALK-Phos and GGT. But you'd look around in other parts of the lab and to see if this was it. And my question to you is what would be higher? The unconjugated before coming to the liver or the conjugated after the liver? And what I just did was probably pretty obvious. It's after the liver. So the conjugated fraction would be pretty high because it's going to the liver, it's just not leaving the body. So anyhow, that's the basics of this. Of course, there's a lot more to learn. There's tons of scientific literature on this. This is designed really to give you more value to get everybody that's attending the weekend seminar, and thank you again so much. I'm so excited about this. To get everybody that's coming in on the same page, whether you're a nutritionist with limited physiological background or a conventional medicine doctor who's been in practice for 30 years and you have tons of knowledge and information on this. My hope to you is that you're learning some new information that you forgot in school or you weren't taught in school. To the nutritionists who may have never even learned this, to have you guys roughly be on the same page so that we can talk about stuff and have everybody, and it's so important to me to have everybody gain so much from this particular weekend seminar. So that's it for now, and I think next video is going to be on the vast number of different electrolytes that are found on a standard blood chemistry. I'll see you there.
All right, so welcome back. Hopefully you like that. Now, as I get this this thing set up here, which I am a male and can only do one thing at a time, even halfway well. Here we are. That's sweet. Hopefully you like that. Now, there's over 5 hours of pre-event learning videos on the lipids and the physiology of the lipids, on the electrolytes, on many of the different wastes like you just saw, on the CBC. We talk about erythropoiesis, and honestly, when I go to the weekend seminar and people come there and they have said that they've watched these videos, they absolutely love some of these concepts on there. We can go so much more deep into the content of the 16-hour weekend seminar, having had people already saw that. So let's go ahead and talk about bilirubin. Now, again, this is straight from the slides of the weekend seminar. You'll know exactly what you get from this. So bilirubin is the breakdown of red blood cell breakdown inside the spleen. Now, during the weekend seminar, I say, you can read through this. I'm not going to read all these things to you. There are almost 1,000 PowerPoint slides. There's no way anybody can get through all these. It's a Cliff's Notes version of physiology at its finest. So I'm not going to read through all this stuff because you guys can read, and that's what I tell people during the weekend seminar. It's a major component of bile, and it's what gives its green pigment. Now, this I'll spend some time on. So we just talked about this, but so here's heme. Now, this component, when red blood cells are broken down, turns into this thing called biliverdin, and then biliverdin in an enzymatic reaction turns into bilirubin. Now let's pay attention to these enzymes because they're actually really important. This first one is called heme oxygenase, and the second one is a zinc-dependent enzyme called biliverdin reductase. Now notice that this NADPH is actually used in both of these pathways. This particular image doesn't say this, and this is important when you talk about the pentose phosphate pathway and glutathione and availability and this awesome reducing agent called NADPH. So here we have heme turning into biliverdin and then bilirubin. Now, I'll show you this in just a second. I'm going to fast forward some of these things. The story that I had about bilirubin was when I went and learned about functional medicine, blood chemistry, interpretation, I was taught that there's no such thing as a low end of bilirubin. Then it turns out, and I'll show you the studies that I saw, when I started looking into bilirubin, that is absolutely not true. That bilirubin right here, this compound right here, is a extracellular antioxidant. And it turns out that bilirubin is not only an antioxidant, but it's an antioxidant against lipid peroxidation. It's a fat-soluble antioxidant. Glutathione, on the other hand, is water-soluble. So bilirubin, it turns out, is this really it is the most potent fat-soluble antioxidant made by the body against lipid peroxidation. So then you think about the phospholipid membrane. That's what's going to have lipid peroxidation. Bilirubin actually protects against this. And what happens is, so if you know a little bit about oxidative stress and free radicals and antioxidants, which I go into great detail in the weekend seminar, is bilirubin can donate an electron. But when it does, and this image doesn't show this very well, is it turns back into biliverdin. So I'm going to go through this physiologically real quickly. If bilirubin donates an electron and becomes biliverdin, and you are testing somebody's bilirubin and it's low, the question is, where did it go? And chances are it's being made just fine, but it's actually being used up, and therefore it's turning into biliverdin, which is not tested for, and therefore is a marker of lipid peroxidation or oxidative stress, which is an amazing marker. So hang tight, remember some of these enzymes, because if we see somebody that has low bilirubin and therefore too much oxidative stress against fat-soluble substances in the body, then the question is, I'll give you a little hint here, how can we increase more bilirubin? All right, so it turns out bilirubin does function as an antioxidant, what I just said, and can be decreased during oxidative stress. Bilirubin is potent against lipid peroxides. It's fat soluble. On the other hand, glutathione is water soluble. During the weekend seminar, I'll just give you a tip. GGT can be a marker of glutathione deficiency or oxidative stress, but that's water soluble. So here we have two markers off of standard blood chemistry. We don't need to run fancy free radical or oxidative stress markers. You have two of them on the standard blood chemistry that, according to the scientific literature, are phenomenal markers of oxidative stress. And I have some great papers to show you on this during the weekend. Because of this, low bilirubin has been associated with a whole bunch of things, including increased all-cause mortality, increased cardiovascular risk. It turns out that bilirubin may be protective against things like diabetes, and I'll show you something on that in just a second. So here's another graphic that I thought was helpful. So heme, once again, via heme oxygenase, and here you can see that reducing agent, NADPH as well as oxygen, turns it into biliverdin. Then biliverdin with NADPH, once again, and this zinc-dependent biliverdin reductase, can turn into bilirubin, which can swing by, if there's oxidative stress and lipid peroxidation, turns back into biliverdin. But that's okay, because as long as we have zinc, biliverdin reductase, and NADPH, we can turn it into bilirubin. But here's a bigger conversation, because down here, this is also showing that glutathione can turn into oxidized glutathione, but we can recycle glutathione as long as we have NADPH. But here's the big question, and we talk a little bit about this during the weekend, is using markers like GGT and bilirubin, if there's a finite amount of NADPH, then perhaps, and if it's because bilirubin's trying to use it all up over here, then maybe somebody can have low glutathione, which might show up as a slightly elevated GGT. This is super awesome stuff. Check out this paper, bilirubin. Now remember, I was told that there's no such thing as low bilirubin, which is not true. Bilirubin, according to this paper, blocks endothelial dysfunction, or the higher the bilirubin, the less endothelial dysfunction, the less vascular smooth muscle cell proliferation, the less hypertension. It's protective against endothelial damage, atherosclerosis, kidney damage, uremia, vascular calcification, cardiovascular disease events, and ultimately all-cause mortality. Wait a minute. We're not paying more attention to bilirubin because we're not taught this stuff. There absolutely is a low end that we need to pay attention to, and I'm going to show you what that range is in just a second. So coming up now is just a bunch of papers. Now, if you're familiar with correlations in the scientific literature, a positive correlation means that if one thing goes up, so too does something else, or if something goes down, then the other thing goes down. So they go together, versus an inverse correlation or a negative correlation means one thing goes up and the other thing goes down, or vice versa. Now, let's take a look at all these papers, and there's so many about these. Bilirubin as a protective factor in rheumatoid arthritis. The lower the bilirubin, the higher the rheumatoid arthritis autoimmune symptoms. Higher serum bilirubin, which is protective, is protective against lower risk for kidney insufficiency in an adult population. So the higher bilirubin, the better. The lower the bilirubin, the more likely non-alcoholic fatty liver disease. This is a great paper over here. So type 2 diabetics are all pretty much going to have an elevated hemoglobin A1C, but it turns out that in type 2 diabetics that have a lower bilirubin have a higher A1C than do type 2 diabetics that have a higher bilirubin and therefore a slightly lower A1C. It's fascinating. There's multiple papers that show that low bilirubin is associated with increased carotid atherosclerosis, decreased blood flow, increased arterial stiffness, and here's one of them. Low serum bilirubin is independently and inversely related to impaired flow-mediated vasodilation, so the blood vessels don't dilate as well, and increased carotid intima media thickness. Bilirubin here, again, was associated with carotid atherosclerosis. Lower the bilirubin, the more carotid atherosclerosis, which I keep going the wrong way. Same here, low bilirubin, worse, more arterial stiffness and less blood flow. And this is my favorite one, is this was looking at bilirubin and all-cause mortality in a fairly large cohort using NHANES data, and take a look at this. So what they used here is 0.6 in terms of bilirubin on a blood chemistry here in the US. That's what they used as the referent. Now notice, depending on the model, the second you went down to 0.5, there's an increased risk of mortality. And if you went down between 0.1 and 0.4, there was an even greater or increased risk of all-cause mortality as well. And what they found is when bilirubin went up, same thing happened, although it wasn't quite as significant. So it turns out that low bilirubin Below zero point 0.5, there's a slight increased risk of all-cause mortality. But when you go down below 0.5, it increases considerably. And this is not the only paper on this. Therefore, here's the traditional range for bilirubin. You can see that that's wrong. And I was taught that this was for functional medicine as well. But anything below 0.5 is an indication that bilirubin is too low. There's probably too much oxidative stress, too much lipid peroxidation, specifically fat-soluble oxidative stress, or which I'll just show you in a second, might be zinc deficiency. And there's more papers on this. So then the question is if somebody has low bilirubin, of course, what do you do about it? Well, one of the things we can do is increase this heme oxygenase, and it turns out there's a whole bunch of papers, a whole bunch of researchers that have been looking into how we can increase heme oxygenase. The problem is, and I'll just give you this quick caveat, is usually these papers, when they're using some herbal or extracts or food extracts, it's done in a petri dish or in some kind of test tube, if you will. And therefore, the actual amounts that they're using might be difficult to achieve. However, we can translate this a little bit into some food type things. So this was if you notice this, the title here, was Identification of Heme Oxygenase Stimulators. That sounds good. So here's carnosol from rosemary, curcumin you're probably familiar with, some green tea extract, and camphorol from skullcap. Now, again, these are cell cultures. And so the amounts that are being used here are probably not attainable through diet alone. However, they're looking at things that might increase heme oxygenase. And the takeaway of this is perhaps we could be giving people some of these foods if we see low bilirubin in them, but we're not done. This was showing that curcumin protected the retinal pigment of epithelial cells against oxidative stress, and it did so via increasing heme oxygenase 1. Here's another paper. Look at the title, Natural Heme Oxygenase 1 Inducers for Liver Function. Here you have curcumin once again, quercetin. These are all compounds from garlic. You may recognize a couple of these here, indole carbinol and sulforaphane from some brassica vegetables. So again, these are cell culture studies. But one thing we might want to consider is, can we increase these compounds in somebody's diet, or might there be some isolated supplements that we can use in conjunction in somebody that has low bilirubin and therefore may have excess lipid peroxidation? One more study, I think. Potential therapeutic effects of natural heme oxygenase inducers, and they're going to be the same things. Here's caffeic acid, curcumin you probably recognize, again, green tea extract, quercetin, resveratrol. In a petri dish, in a cell culture, all were shown, or I think some of these might have been mouse studies, were shown to increase heme oxygenase and therefore bilirubin. And I want to make one quick caveat to this. You can go ahead and read this. Now, polyphenols actually increase bilirubin, it's been shown, food-based polyphenol. But it does so by blocking bilirubin's metabolism or excretion out of the body. So polyphenols might be helpful as well, although it's not by making more bilirubin, it's by blocking bilirubin from being broken down in the body, which doesn't fix the reason why it was low in the first place. It was probably being used up because of the peroxidation. Anyhow, we're going to finish this up here. Bilirubin, if it's high, and by the way, in the weekend seminar, you get dozens of these blue tables, which is essentially telling you when a marker is high or a marker is low, why, the physiological reason behind why, and what you can look at to go deeper into ruling in or ruling out if that's a potential cause. So if you see bilirubin above 0.8, which is the optimal reference range, I think based on the evidence-based literature, it could be excess hemolysis. This is red blood cell breakdown. What's the process? Well, if red blood cells are being broken down, then heme's spilling out of it. And what else can you look at, which we talk about during the weekend seminar, that you can rule in or rule out? Hemolysis was why somebody had high bilirubin. You could look at the CBC, low red blood cell hemoglobin hematocrit, MCV, MCH, MCH is probably normal. Might be high LDH, might be high potassium or magnesium. The other thing is it could be liver dysfunction. Now, this is probably pretty serious liver dysfunction and maybe not something you might see in a functional medicine practice. Could be bile duct obstruction. Bilirubin is not being excreted where it's supposed to in the biliary tree. Or there's something else called Gilbray's syndrome, which is a genetic condition that causes high bilirubin. How do you know? Ask them if they've had bilirubin before. If they say yes, every single time I've had my blood done, then that's probably what you're looking at. On the other hand, if bilirubin is below 0.5 or 0.4 or below, it might be due to oxidative stress, specifically due to lipid peroxidation like we talked about, or zinc deficiency because biliverdin reductase is a zinc-dependent enzyme. How can you find out? Alkaline phosphatase will tend to be low also in zinc deficiency. They may lose a little bit of their taste acuity. Things don't taste quite the way that they did before. So if somebody has decreased bilirubin, then you want to consider perhaps giving them some of these things. Now, I'll be super honest. I haven't found any papers on vitamin E as it pertains to bilirubin. Unfortunately, really disappointing. But when you consider that vitamin E is one of the most deficient nutrients, micronutrients, especially in America at least, in intake, meeting the RDA. In fact, that's pretty much on the top. And vitamin E is a fat-soluble antioxidant, that it makes sense if you see low bilirubin, and that's a marker of lipid peroxidation, that vitamin E would probably be indicated. We also saw a number of papers that looked at curcumin, garlic, quercetin, maybe sulforates, anything, brassica vegetables, but addressed why there's potential lipid peroxidation in the first place. So at this point, I'm going to end it now because hopefully you have a sense of what now rinse and repeat. You want to do that for uric acid and GGT, alk phos, AST, ALT, all the electrolytes, sodium, potassium, chloride, CO2, all the markers on a CBC with differential, including platelets, including the lipids, including mitochondrial dysfunction, detoxification, glucose dysregulation, and so much more. I hope to see you at the weekend seminar. Hopefully you found this helpful, but now you have a sense of what's covered. And I will just add one more thing. If you want to see what other people are saying, click on the link below and it'll take you to another video. Thank you so much and have a really blessed day.